Okay, today we're going to be talking about the closure property. Reasoning, examples, and counterexamples. Mathematical closure. That's defined as you need two things, a set of numbers and an operation. So a set of numbers is said to be closed under an operation if any two numbers from the original set are then combined under the operation and the solution is always in the same set as the original numbers. Okay, so what does that mean? So you need a set of numbers. That's just a group of mathematical objects that have a description. In this case, in this first example, our set is even numbers. 2, 4, 6, 8, 10, 12, etc. But also negative even numbers, -2, -4, etc. You have operation, addition. So what you're doing is you're saying, okay, is this set closed under the operation or not? So in this example, is the set of even numbers closed under addition? Okay, for this to be true, and the answer to be yes, basically, you need a member of the set, and then a mathematical operation, and then another member of that same set. So you're taking two members of the set of numbers and you're combining them under, it's called, that's the verb, combining under this mathematical operation. So you take an even, you add another even number, and then the mathematical outcome is an even number always. Meaning like, I take an even number, I use addition, I add another member of the set, another even number, I'm always going to get an even number. So, in other words, is an even number plus an even number equal an even number always? Well, you just need to sort of try to do some thinking, think of examples, or counterexamples, potentially, which we're going to see in a moment. But in this case, an even number plus an even number equal to an even number. Let's see. What do we know? Any even number. Let's take 4, an even number like 4, and then maybe we'll add 6. All right, what's the outcome there? 10? Right. Okay, good. Even plus an even equal an even. That's just one example. We need to possibly think about more. Are there other examples? Is there a counterexample that would disprove this? A counterexample. That's a special kind of example that disproves a statement. You only need one counterexample to disprove this situation. So 4 plus 6 is equal to 10. That's an example. That's an even plus an even is equal to even. Is this always true? Let's take 12 and add 6. That's 18. Another example, not a counterexample. It turns out every even plus every even is going to be an even number. So is this true always? Yes. This is definitely true always. So what we can say is that the set of even numbers is closed under addition. So that answers our question. Is the set of even numbers closed under addition? Yes, the set of even numbers is closed under addition. Okay, next example. What about the set of odd numbers? Also the operation addition. Is the set of odd numbers closed under addition? So for this to be true, this is a member of a set. Take an operation, addition, so we're adding another member of that same set, and then is our outcome an odd number always? Well, let's check this. So here, I am just going to say 5 plus 3, 2 odds, right? Add it together. What's that outcome? 8. Oh, well, that's not an example. This is an odd plus an odd is equal to an even number. Well, that's not going to work. That is a counterexample. And you only need one. You just need one. Because you're trying to say, is an odd plus an odd always? No, in fact, an odd plus an odd is actually always an even. But all you need is really one counterexample to say definitively no. And then beyond that, we're answering our question here and saying the set of odd numbers is not closed under addition. So we have concluded that because you can't take a member of the set and then combine it under an operation, odd plus an odd, and then always get an odd, and the outcome is always odd, because that is not true, we've come up with a counterexample, then the conclusion is the set of numbers is not closed. Odd numbers is not closed under addition. All right, so let's look at some additional examples that more pertain to our unit, right, that we've been talking about. Rational and irrational numbers. The set of numbers on this portfolio test is going to be rational and irrational. So is rational numbers closed under addition? Well, let's try to think of examples or counterexamples. It turns out, yes. Here's an example. 2/3 plus 5/6 is 3/2. But any two fractions, basically, that you add, the outcome will be a fraction. You'll never get an irrational number. So for that reason, is the set of rational numbers closed under addition? Yes. And this is an example, right? Not a counterexample. But you could come up with many other examples. Is the set of irrational numbers closed under addition? In this case, no. All right? It's not closed under addition. And here's why. You can take an irrational number and add an irrational number, right? And your outcome is a rational number. So let me repeat that again. An irrational number like pi and another irrational number, the outcome is 0. 0 you can represent as an integer over an integer, right? 0/5 is an example. That can be a representation of 0. It happens to be that an irrational number and its opposite is a good example of irrational numbers not being closed under addition. But the answer to this is no. Rational numbers closed under multiplication. Try to come up with examples. Let me see. Every fraction times every fraction is going to be equal to a fraction. And here's why. Look, something like 4/3 times 2/5, you're just multiplying numerators, 4 times 2, multiplying denominators, 3 times 5. So every single multiplication of two rational numbers, you're going to get another fraction or another rational number. So for that reason, is the set of rational numbers closed under multiplication? Well, in this case, yes. Last one. Is the set of irrational numbers closed under multiplication? So irrational numbers? Well, let's try to think of some examples. Sorry, this last one as well, too, was an example. And this is a counterexample, so just to be clear. So the set of irrational numbers closed under multiplication? Well, let me try to multiply some irrational numbers down here. Just gonna come up with one here. Let's see, √3 times √5. All I do is multiply the radicands, and I'm gonna get √15. Okay, that's an irrational times an irrational is equal to an irrational. So is it closed? No, not closed. Not every irrational times an irrational is going to equal an irrational. Look at this. Look at this example. Or sorry, this is a counterexample. √27, an irrational number, times √3. An irrational number is √81. Well, what is √81 equivalent to? √81, right? √81 is 9. That's a rational number. So this, my friends, is a counterexample. So there are some irrational numbers. As long as the radicands multiply to a perfect square like 81, then you can take the square root of it and get 9. So this answer is no. The set of irrational numbers not closed under multiplication. Okay, so we're going to be applying these concepts on this portfolio test. We're dealing with irrational and rational, but I could ask you if it's closed under any operation, and you should be able to come up with a cogent answer.